Swayam Prabha. Digital India. Educated India.
So welcome back. In the second lecture, we'll be talking about probabilistic and Bayesian models for solving regression problems. So this is sort of a more real problem as compared to the Gaussian mean estimation problem that we were looking at in the previous lecture. I believe you have been, taught linear regression in one of the previous, lectures. So linear regression everyone has seen, right? So what we will be doing in this lecture is that we will look at how to set up regression problems, both linear and possibly non-linear regression problems, using probabilistic or Bayesian models. We have already seen what are the basic components of a probabilistic models, so how we can use those components to build a probabilistic models for solving regression. So just as a background, I'll come to that. I'll come to that, right? So, I think the reasons are similar to what we already saw. We need, basically, we are learning a model here also, so we need some notion of uncertainty in what our model is, right? So we are learning a weight vector in the regression case, right? So we need to know how certain we are about the parameter, the weight vector, right? Also, when we are making prediction, we need to be we need to have some estimate of how certain our predictions are, what is the confidence, in our. Yes. And also we will see that there are some connections. In fact, you can look at the probabilistic models and under some approximation, you can think of those as non-probabilistic models. We will look at all these things, just bear with me. Anyway, so let's start with some background on linear regression. So in linear regression is basically a supervised learning setting where we are given training data in form of n IID training examples that I'm denoting as x and y. And so these pairs are our inputs, basically, inputs and outputs. Each xn is a feature vector in d dimensions, and since we are doing regression, each response yn is a real value. Okay, so regression is real valued response prediction problem. So again, feature vectors are d-dimensional. Capital D denotes the number of features in the input, and scalar is response is scalar. Okay, and when we are doing linear regression, we typically assume a linear relationship between the inputs and outputs, and this relationship is parameterized by a weight vector w, which is again a vector in d dimension, and we say that yn is approximately w transpose xn. So yn is the response, xn is as the input, and the relationship is roughly linear. Okay. So this can also be written as yn as approximately equal to sum of wd times x and d. X and d is basically the dth feature in the nth data point. Okay, so this is the relationship between the input and output of the nth training example. So this holds for all the n data points. Okay, so this is basically a linear model. And as I said, w, which is basically a d-dimensional vector, is the regression weight vector, and this is the unknown that we will be trying to estimate. So how do we estimate this is what we're going to look at. You can also think of the weight vector, w, so as something where the dth component is telling us the importance of the dth feature in the data. So wd is how important the dth feature is in making the prediction. Okay. Now, if you have seen the non-probabilistic model for solving regression, we typically define a loss function, which can be both either an unregularized or regularized. Okay? So if you have an unregularized loss function, you basically have a least squares objective. Okay? So you solve for the optimal w by solving this least square problem, where the loss function is defined as the sum of squared errors of the truth yn minus the prediction w transpose xn. Okay, and you have a squared here, and this is the loss function on one data point, and you have a summation over all data points. So this is your objective function or loss function, and you find the optimal w by minimizing this objective function with respect to w. Okay. Again, in order to solve for w, you have to take derivative with respect to w, set it to 0, and then that gives you the solution. You might have seen this solution in the previous lectures. The solution has this form. It's basically sum over all the data points, xn transpose inverse, sum of all data points, xn times yn, which also has this matrix vector notation, x transpose x inverse x transpose y. Okay, so I believe if you have seen linear regression, this is the final solution. So the solution is x transpose x inverse x transpose y. So note that this capital X is the n by d data matrix consisting of all the So think of X as a matrix where each row is an example. Okay, so capital X is this n by D matrix, and this bold-faced Y is the vector of all the responses. So this bold-faced Y is then n by 1 response vector. Okay, so this will give you the solution for the weight vector W. Okay, so I believe you have seen this expression before. Raise your hand if you have not seen it. Yeah, I trust everyone has seen it. Okay. So note that this requires an inversion. So X transpose X will be a D by D matrix because X is n by D, so X transpose X will be a D by D matrix. So the result will be a D by 1 vector. This is the D by D matrix inversion times basically X transpose Y. So the overall result will be a D by 1 vector, column vector, which is what your solution will be. Okay. So this formulation doesn't have any regularizer. Okay. You can also come up with a regularized version of the same problem where you add this L2 regularization, where you have an extra term of the form W transpose W, and you add a regularization constant tau, okay? Or sometimes you just use a lambda here, okay? So again, raise your hand if you have not seen this regularized version when looking at least square or linear regression. You have seen it, right? So this is a minor variation from the first case, where you have this additional term in the loss function, W transpose W. And if you solve for this objective, you get a solution that looks something like this: X transpose X plus tau times I inverse X transpose Y. Okay, so we prefer this form because it has a regularization aspect to it, so it can prevent overfitting. Okay, so both. So the first one is unregularized loss function minimization. The second is regularized loss function minimization, where Yn minus W transpose. The first term is the loss function. The second term is the regularizer, and the solution looks something like this. Well, okay. So if instead of a tau, I have no. I think this is like fine. This is tau times I. Yeah. So you can verify this. Okay. Okay, so anyway, so this is the non-probabilistic version of linear regression. So you can solve it, you'll get these solutions. Okay. However, we are talking about probabilistic modeling. So how can we set up this problem as a probabilistic model, and what are the benefits of probabilistic modeling if we solve linear regression using a probabilistic model? So let's first look at the formulation as to how we can set up this problem as a probabilistic model. So essentially, we are looking to design a model where we have an output Yn, which depends on the input and the weight vector. Okay, so you can see. So this picture that I've shown you is a basic, simple, directed graphical model where the direction of arrow shows the dependence. So this arrow pointing towards Y denotes that Y depends on W. Likewise, Y also depends on X. And this rectangle with an N shows that there are N copies of the data. So there are N data points. Okay, every data point has this relationship. Every output has this relationship on the feature vector and the weight vector. Okay. Now we are going to set this up as a probabilistic model, as I said. So we need two ingredients here. First of all, we need a likelihood model, right? If you recall our discussion from the previous session, we had a likelihood model for the observations, and we had a prior distribution over the parameters. What is the parameter here? What is the unknown here? W, right? So W is our parameter, right? So, and what is the observation here? Okay. Now, there can be divided opinions whether our observation is just Y or both X and Y. Okay. Now, it depends on the way you are modeling the data. In this case, we will only model Y. We will treat X as a fixed thing that we are conditioning on, that Y depends on. Okay. So our probabilistic model or the likelihood model will be defined just on Y given X. Okay. In some other models, you can actually model X also, but in this case, we can simply say that we are modeling the predictions, the responses, right? They are functions of X. Okay, so this is also known as a discriminative model. If you want to differentiate with models where we also model X explicitly. Okay. So anyway, so this is the model. So we have a known parameter W that we are trying to estimate. So we will have a prior distribution P of W. We have observations Yn. We will have a likelihood model of the form P of Y given the parameter, right? So note that what is the form of this likelihood? P of Y given the parameter W. Since it also depends on X, so we are also conditioning on X. So this is just a notation that I'm using. Okay, but you can even suppress the X here. You can just say that it's P of Y given X, P of Y given W. But since we are also making Y depend on X, so I have explicitly kept X in this notation. Okay. Yeah. So as I said, we would, in order to set up a probabilistic version of this model,